Next up, we have Lars Fritsche, fan favorite, from a cryptic email to enduring impact, a decade of working with the Michigan Genomics Initiative.
Hello, everybody. So when Sebastian asked me, hey, can you give a talk about the exciting research you're doing right now with MGI? All I can think of about the exciting research I was doing, because at that time I don't have an exciting project to share with you, so it's all about nostalgia today. There are not many people around here that started with me. I see Chad. I'm very excited to have him here. And he was actually part of the first cryptic email that I got from Gonzalo about this. So I hope it's okay to share some of the content. Go for it. Okay, I've been around and I worked with this, I think, since 2013. And what I'm showing here, it started with this kind of email. Forward SOP for genotyping QC. And then Gonzalo said, I'm going to send you both an email that will explain this one. And we got basically Affymetrix data, Illumina data, and the person from the DNA sequencing core, now the advanced genomics core, said, hey, please let us know if you have any questions. And I had many questions what this is about. And if you know Gonzalo, this is kind of what he does. He copies you on an email, and you're supposed to figure out what you're supposed to do. And so the next email followed 10 minutes later, and it just said, work. And this was not to me, but it was to Greg, who was a fresh PhD student just starting at that time. And he said, hey, hope semester is going well. And we have an exciting project combining genotype information with health records for large research studies. Here's the pilot data. Xiaowei and Lars, Xiaowei was a PhD student at the time, said, we know where to get the data. Lars will give you pointers to the QC analysis. I'm about to fly to China. Do it. And so it's an excellent example of leadership. And Gonzalo is fantastic to know he has people around him that figure out what to do. And so the early milestones were kind of to explore which platform we're going to select. And so we had the choice between Affymetrix and Illumina. And Greg was a fantastic student working this out with me. And basically Illumina, and shout out to Illumina, outperformed Affymetrix quality scores in every aspect. They had fewer markers on the array, but with imputation it outperformed Affymetrix, and that's how we ended up with the Illumina platform. And so then there was a period when Wei Zhou, part of, I think also Gonzalo's lab, Kristen Willer's lab, and also the Hunt team, they designed the custom content for human core exome chip. And that's the reason why, so there's a Norwegian connection in here. Whole genome sequencing study informed what exciting variants they wanted to include, and that's why the first area was called Hunt. Hunt, that's the Trøndelag Health Study. And so, in January 2015, the data came in, and so what we are supposed to do now is to figure out the quality control pipeline. There was none in place, and this was work done by Gonzalo's group, anesthesiology, Chad's team, the DNA sequencing core, and we're doing sample quality control. That was basically on the fly to give early feedback. There's Gonzalo. Hi, Gonzalo. Just shared a few emails from you. That was okay. And so this was on the fly, and so to kind of realize if there are any sample handling issues, so we can react in time, figure out what's happening, improve, and then we came up with those data freezes that we have we stick to round numbers at 10,000, 20,000. That's when we kind of pulled the data together, called it together to increase quality. And then in September 2015, we got final IRB approval to combine the genetic data with the electronic health record data, and Erin was fantastic help with us. And so it took a while to get to the point where we can actually do analysis. But so I'm a statistical geneticist, and I have never worked with electronic health data before, and said, oh, now you can combine the data, and then, oh, how to do this? And so we were fortunate to have this PWAS-R package at that time that was already, I think, 5 years old. Basic idea is to use diagnosis codes that describe the similar phenotype and kind of combine this and say these are the cases. If there are some similar diagnoses that don't really are cases, you don't want to include them in the analysis, and everybody else will be considered a control. And that's a very rough definition of phenotypes. And so here's just an example. We can use ICD codes for melanoma. Then there are other skin cancer types that we do not want to analyze as cases, but also we don't want to include them as controls, and then everybody else, if they were screened or unscreened for skin cancer, were included in this case control study. And this R package really takes the pain out of this. It's very easy, but the question is, how good are those phenotypes? Initially, we thought, okay, let's look at the distribution of those phenotypes in MGI. What are we actually seeing? And what we saw is that MGI was highly enriched for cancer, and about 50% of patients were affected by at least one form of cancer. That was surprising to us. We didn't know what to expect, but it had to do with the recruitment mechanism, people undergoing surgery, having biopsies, and people with cancer obviously are more likely to have biopsies and surgery, and that kind of explains some of the enrichment we're seeing here. Then in 2016, I ran a few tests with the GWAS catalog data. So these are validated variants. How do they perform in MGI? And so we are looking here at one SNP, and this is a phenome-wide association study across the phenome we just generated. And you can see that this SNP is highly associated with skin cancer. This was positive, but then also other things are showing up that might be related to skin cancer, might be related to the diagnostic methods. But this was a very positive result. And the question was, okay, we can see small p-values. This is great. I like those plots. They are very colorful. How good are the actual effect sizes? And so we also did an analysis looking at GWAS catalog results. How do our effect sizes compare to the published effect sizes from those large papers, those large meta-analyses? And what I'm showing here is melanoma of skin, and what you can see, this nicely lines up. The correspondence is very high, and I picked this example because it looks like nice, and it doesn't work all the time. Sometimes the phenotypes with the PWAS code are not that good, and we can't really find equally strong effect sizes. But when it comes to cancer, it seems those diagnoses are very valid, and maybe it is easier to find cancer patients with ICD codes, and so that became one of the main focus of my research going forward. And Gonzalo had the vision saying, hey, you can do this here, and this was an interactive plot. I still have the web page, and he was fascinated by this, and then said, hey, wait, you can do this with one SNP. Let's do this for all the SNPs that we tested. And so he came up with the idea to have GWAS times PWAS, have an interactive interface, and he had a very smart web application programmer, Peter, and he put together the PWeb, and that was later published as this Nature Genetics correspondence, and that's the PWeb that everybody's using and loving today. And so the main research themes about my research in MGI was basically using MGI as an independent cohort. We were doing this since 2017, but then here I'm going to focus on polygenic risk score analyses, how we are using MGI to generate them and to evaluate them. And then, because we like PWAS plots so much, we're doing PRS PWAS. So instead of testing a single variant, we're using a polygenic risk score to see what is associated with this polygenic risk score. And we're using large biobanks, MGI and the UCA biobank. And then there was another chapter where we dealt with COVID-19. And as part of Brahma's group, we were very ambitious and curious to use the electronic health record data to get some insights about COVID-19 and risk factors. So when we talk about polygenic risk scores, the basic idea here is that we have such a nice Manhattan plot, and this is prostate cancer, and we can see many hits here. And so how can we use this for kind of maybe clinical utility? Can we use this information? And so there are many software tools out there that can generate polygenic risk scores from the GWAS result. And maybe you'll find such an excellent polygenic risk score you're seeing here, where you have a nice shift. So you basically have one risk score per individual. And when you plot the cases versus controls, you can see this right shift of cases. You basically can also see the issue with polygenic risk scores. They are not good for individual level prediction. You have this massive amount of overlap here in the middle. But what you can see here is that in the tails, you have an enrichment of cases. And I think that's one of the main benefits of using polygenic risk score. You can kind of enrich cases in the tails of that distribution. And so that is the main point, and we were excited to have those excellent results from, for example, prostate cancer. And then one of the questions is, there are so many polygenic risk scores out there, which one should I choose? And so there's a project I did with Randy Vince in urology, also with Todd Morgan. And so we were looking, in this case, at 16 different published polygenic risk scores for prostate cancer, and we're interested, how do they perform they were, what is an indicator for their performance is when they were published, the method, and we didn't know at that time. And basically we looked at this, and this is done in MGI, looking at almost 3,000 prostate cancer cases and 15,000 control, unrelated European ancestry. And what we found is that there's a wide spread of their performance in terms of their association signal, so very nice small p-values, but it's quite a range, and even considering that they were published at the same time. So obviously polygenic risk scores is not straightforward to use to identify what's the right one, and so we identified there's kind of a need to have those comparisons to be able to pick maybe the most powerful PRS for your own cohort. Another result from this study was that yes, we can enrich a certain phenotype in the tails, but can we use them for something else as well? Is there clinical utility, for example, to identify prostate cancer cases with high aggressiveness? And so in the collaboration with Randy, we used the Michigan Urological Surgery Improvement Collaborative Music Registry, combined it with the MGI data through the data office and Aaron's team. And we used the pathology and biopsy-based aggressiveness scores on prostate cancer to get an idea how does this align with this polygenic risk score we identified performs very well. And what you can see here on the top, these are the three different aggressiveness classes, and you can see there's virtually no difference between their risk scores. The distributions all up nicely, but they're all somewhat larger and trend to be right-shifted compared to the controls on the bottom. So basically, for aggressiveness in prostate cancer, those PRS that we looked at did not help to differentiate between indolent and aggressive disease. So the big question that we had is, how do we select a suitable polygenic risk score? What's the best external GWAS we can use? Which method should we use? Is the one method and GWAS combination the best for everything we're going to do with the polygenic risk score, or are there differences if you want to look at associations, if you look at discrimination or risk stratification? And so there's a need for a comparative assessment, and we found that MGI and leukobiopsy is an ideal platform for this. And so what we created was, and thanks shout out to Snehal for helping with the online platform, PRS Web. Basically, the idea was we compiled a list of all the different summary statistics we can find for all the cancers for which we had sufficient sample sizes in leukobiopsy and MGI. We used the state-of-the-art PRS method at that time and constructed 1,300 PRS, tested them if they work, and we found over 500 of them were associated with the primary cancer. So these were not great PRS, but they were associated, at least their effect sizes went in the right direction. And so we had a collection of 500 PRS, and describing 500 PRS and their PFOS result is a pain, so having a platform is nice to allow people to browse through those results, look at the evaluation, rank those PRS based on their performance metrics, then also look at interactive PFOS plots, and also download those PRS. And so basically we created this platform, and those links were working a few months ago, but there was an update on the server, so they're under maintenance until next month. But the basic idea here is that we have an interactive table where you can type in your trait of interest, you get all the scores we generated, you can rank them based on your favorite metric, and select that polygenic risk score. Then you can look at the phenome-wide association plot, see how specific this PRS is associated with your trait of interest. Are there any other traits that might be relevant for covariate selection? And then you can also download those the weight files. And we did this for 35 different cancer traits, but then also expanded to health-related exposures like BMI, smoking, lipid levels, and they are all part of such a platform. And we found this to be a great tool, and people like this, and we're using those PRS as well. And here's just an example for a PFOS plot. When you look at the skin cancer polygenic risk score, in this case this is for cutaneous squamous cell carcinoma, you can find it's highly associated with skin cancer, but also some other dermatological traits. And we found that one of those traits, actinic keratosis, for example, has a shared genetic component to, and so this is independent from this. It's not independent, but this is kind of a precancerous phenotype you can identify through that PRS. And I found this is a nice story. And we have 4 papers that came out of this work using PRS for FIWAS. We have those 2 PRS web interfaces. And shout out to Yin Ma, who was GSRA in my lab, and she did a lot of work on she basically did all the work on the XPRS web. So we generated over 800 polygenic risk scores, and at the same time there was the PGS catalog that came out, and so basically they also had the idea, hey, we should share those PGS, widely harmonize them with the community and share them. And when we uploaded our PRS, we basically 50% of all the PRS in this platform came from Michigan, which was a nice feat, and still it's about 20%. And basically you now can go in there, so we deposit our polygenic risk scores, you can go in there, download them. And the biggest downside of this is the performance metrics. All they're reporting are the original performance metrics of the original paper. So there's no way again for you to determine which one is the best PRS. So there's a place for a platform like PRS Web that we set up. And maybe we'll pick up on that at some point in the future, but MGI is now used also excessively in biobank studies and meta-analysis. So it's not always independent, so there's an overfitting issue, and that's something else that we can figure out in the future. Okay, so lastly, I just want to mention the COVID-19 research we were doing, led by Brahma in the Center of Precision Health and Data Science, and these are just some of the topics we worked on, where I had kind of a co-lead position, and we were using the electronic health record data, the de-identified electronic health record data, and that was a fantastic resource to have at that time. Basically, it allowed us, and we had a very strong, motivated, and talented team of smart students that were interested in this kind of data. They wanted to contribute to to understanding of the pandemic, and so we had timely access to the latest EHR data. And the key for the high productivity of that group was that we had a kind of a centralized data harmonization. So instead of throwing the EHR data to every student and say, figure out what to do, we kind of figured out it's probably best to have this done by me, because I was familiar with EHR data and they can focus on the science, and that allowed them to study all those features. And and that's kind of the thing here when we talk about combining EHR data with genetics data. Genetics data is great, especially if you have somebody like Brad preparing the data in such a sophisticated way. You have all the features you need. You have the principal components. You have the inferred ancestry. You have the relatedness that makes this straightforward to integrate. But when it comes to the phenotypes, you need all those additional covariates. And phi codes, again, that is easy. You just plug in the ICD codes. You run this R package. Great. You have your phenotypes. But everything that goes beyond that is tricky. If you have a time component in there, things do not line up nicely. This data was not meant for research purposes. And so I'm looking forward to the time when we can use maybe a standardized version of the EHR data, maybe use large language models on this data, because cleaning big data is the most time-consuming and the least enjoyable part of data science. And we know this for quite a while, so this article is quite old. And I talked to Sachin Ketapal, and he said that they are working on standardizing the EHR data to OMOP standard, but then also to maybe allow us to use large language models to help mine this data more efficiently. And so MGI had a huge impact on my career, my research, but also on collaborations I was able to join. And so this was my cryptic email in 2013. First FIWAS was generated here, and over time it helped me to kind of also have some experience in Norway. They used the same platform that we used for MGI, so that was helpful. Later also was awarded a Precision Health Investigator Award to help with the PRS pipelines. And we created many publications, many collaborations, and I'm very thankful for that, and that had a huge impact for me. And so special thanks to all my collaborators, Gonzalo, Ying, Brahma, Randy, and also Chad. And I'm showing here just the co-author network that opened up through my direct interactions with the MGI data. And yeah, thanks for your attention.